So we come to our last section of the entire course. This section will cover chapters 10, 11, and 12. It's about heat and thermal physics, okay? And if we get time, chapter 12 will be thermodynamics. We may or may not get there. So in this chapter, in chapter 10, we will do, again, only 4 sections, section 10.1, 10.2, 10.4, and 10.5 of the book. Thermal physics is the study of temperature, heat, and internal energy. And I'll define each of these things for you. So by the end of this chapter, you should have a clear idea of the difference between these terms. Heat basically leads to changes in internal energy. So what is internal energy? Say you have a gas, right? Then you might have some interactions between particles. Those interactions, those bonds, are holding potential energy. Yeah? If the gas molecules or atoms are moving around, which they will be in a random way, then that kinetic energy is part of the internal energy. So any kind of energy inside your system is called your internal energy. Okay? And that internal energy is intimately related to the temperature. The higher the temperature, the higher the internal energy. We typically write internal energy with the symbol U. Yeah? The temperature is represented as T, and we'll see in a minute what heat is. There's no symbol for heat. Okay. We will learn about gases towards the end of this chapter because gases are critical for harnessing that internal energy to do work. Okay, so they can store internal energy and they can release it. And we can use that energy to do work. First, we start with some definitions about what is thermal contact. So objects are said to be in thermal contact if there can be energy transfer between one object and the next. Okay, so they may or may not be in physical contact. You may have physical contact, but if you have perfect insulation, then there is no no energy exchange possible. Then they are not in thermal contact. So thermal contact is defined as the process by which energy is exchanged between two objects, okay? Then they are in thermal contact if they can exchange energy. And heat is the process by which that energy is exchanged because of temperature difference. So whenever, let's say the object in this hand is warmer than this hand, then heat's going to flow from this side to this side, yeah? From the higher temperature to the lower temperature. This is our everyday experience. So that flow of energy is called heat. Okay? So heat is not contained within an object. Heat is not possessed by an object. Heat is that flow of energy due to temperature difference. Okay. Thermal equilibrium is achieved when both the objects are at exactly the same temperature. If they're at the same temperature and they are in thermal contact, now no energy needs to be exchanged between them because they are already at the same temperature. That defines thermal equilibrium. Okay? So let's say I have an object A and an object B, each of which, let's say object A is in thermal equilibrium with this object C, which happens to be a thermometer. So let's say the thermometer is reading 22.5 degrees Celsius, and that is the temperature of the thermometer and the same temperature for object A. So these two are in thermal equilibrium because they are in thermal contact. Now let's consider a separate object B, and it's again, now we move that thermometer here, and it's still at 22.5, and let's say it's in thermal contact and thermal equilibrium with B. So that means A and B are at exactly the same temperature. So if A comes in contact with B, then there's not going to be any thermal exchange between them because they are at exactly the same temperature. Then we have thermal equilibrium, right? This is my zeroth law of thermodynamics. So the zeroth law says that if objects A and B are separately in thermal equilibrium with the third object C, then A and B are in thermal equilibrium with each other. Object C could be a thermometer. Yeah? So this might seem something obvious. It's like saying if A equals C and B equals C, then A equals B. Yeah? But this allows us to define a temperature and temperature scale. So it's important, okay? There are 3 laws of thermodynamics, first, second, and third, and this is the zeroth law, okay? In addition to those 3 laws. The other 3 laws of thermodynamics we will come to in chapter 12. Okay. So this temperature from the zeroth law says that temperature is the property that determines whether an object is in thermal equilibrium with other objects. Yeah? If we have thermal equilibrium, there is no heat, there is no exchange of energy. 2 objects in thermal equilibrium with each other are at the same temperature. Okay, so we've understood thermal contact, thermal equilibrium, and temperature. Now, there are several scales. So now we come to the different scales of temperature. And the scale that we use in the NKS SI system is going to be called the Kelvin scale, after Lord Kelvin, who did a lot of work on heat. Okay. He was a Scottish gentleman from Glasgow. Okay. So when we define a temperature scale, any temperature scale, we define 2 points and we divide into certain units between them. Yeah, usually equal units between them. Equal number of divisions, so a certain number of divisions of equal width. So here the first point is going to be the absolute zero, which is called 0K, K being short for Kelvin, so 0K, which is the same as saying negative 273.15 Celsius. So Celsius and centigrade I use interchangeably, okay? And usually we write a degree Celsius, okay? So let's, that's the convention. Here I've missed out the degrees, so I'm just gonna put it by hand. When we write Kelvin, we do not write degree Kelvin, we just write Kelvin, K, okay? That's just convention. So the lower point is 0 Kelvin, and the upper point is the triple point of water, which happens to be at 273.15 Kelvin or 0 degrees Celsius. So you might be wondering, what is triple point? Triple point is where the 3 states of water, solid, liquid, and gas, that means ice, liquid water, and steam, all coexist. That means at a certain temperature and pressure, it's possible to have all 3 states occurring. To show different states, you plot what's called a phase diagram, which looks something like this, which shows different pressure on one axis, temperature on the other, and you have different states of water occurring here. Okay, this is a diagram for water. So S stands for solid. That means we have ice in this side, in this region. This is liquid water, L, and this is water vapor or steam over here. So you see at this point, the 3 lines meet. We have triple point, which has a temperature of 0.01 degrees Celsius and a very low pressure of 0.006 atmospheres. Yeah? You do not need to memorize. You don't really need this diagram, but it's just nice for you to recognize what triple point is. So I gave you this. You do need to know the 2 points of the Kelvin scale and their values, okay? And these 2 points are divided by 100 divisions, 100 equal divisions. So the Kelvin scale is similar to 2 other scales that we use. One is Fahrenheit scale, which we'll look at next, and the other is the Celsius scale. So the Kelvin scale is very similar to the Celsius scale or the centigrade scale. It's just shifted they're shifted with respect to each other by this much, by 273.15 degrees. Yeah? So Kelvin temperature equals Celsius temperature plus 273.15. So Kelvin is always a higher number. You'll need to know this formula. Okay. Give you a feel for different temperatures. Here we've plotted several different temperatures on this logarithmic scale. You can see it's varying by powers of 10. So it's a logarithmic scale. Yeah. Although it looks linear, if you look at the the readings of each line, it's not linear, it's logarithmic. Why do we use that logarithmic scale? In order to show a vast range which would not otherwise fit on a piece of paper. Okay, so temperature in Kelvin is shown here, and to give you some idea, hydrogen bomb produces very high heat, 10 to the power 8 Kelvin. Yeah? Solar corona, or let's look at this, the interior of the sun, which you'd expect to be very high heat, 10 to the power 7. Yeah? Let's go down, water freezes at just above 100 Kelvin. Yeah? And as you go lower down, you get liquid nitrogen, liquid hydrogen. So gases, which are normal temperature, they're gases, at very low temperature, they're turning into liquids. Yeah? Hydrogen, nitrogen, these are normally gases at higher temperature, at room temperature. And then lower still, you get liquid helium, around 1 K. Yeah? And we've achieved the lowest temperature of 10 to the minus 10 Kelvin. Note that we have not achieved 0 Kelvin, which is the bottom of the Kelvin scale. Yeah? So we can never attain that. That's called absolute zero. 0 Kelvin is called absolute zero. It will never be reached. It means that all vibrations stop. I told you in solids, remember, you have atoms which are held in position, maybe in a lattice, and they're constantly vibrating about their mean position. Yeah? So all that vibration has to completely stop. Everything will be perfectly still at absolute zero. And we have never attained that. Okay. So next, let's look at the Fahrenheit scale. This should be quite familiar to you. So we say that the 2 points of interest are the ice point where water freezes, which is 32 degrees Fahrenheit, and the steam point where water boils, it's 212 Fahrenheit. Yeah? And we have 180 divisions between them. So on the Fahrenheit scale, we do not have 100 divisions. Hence, we're not going to have a simple addition or subtraction to be able to move from the Fahrenheit scale to the Kelvin scale or the Celsius scale. It has to be a more complicated expression. So if we look at the 3 scales together, here's the Kelvin scale. And remember, it's exactly like the Celsius, except it's shifted. So where we have 0 degrees centigrade here at the ice point, freezing point of water, we have 273.15. You have to add the 273.15 to get the Kelvin value. And the boiling point of water, 100 degrees Celsius, add 273, you get 373.15. Yeah, that's the other point shown here. What about the Fahrenheit scale? This one is different. You see the divisions are different. They do not line up with these, yeah? Nor on this side. So freezing point, 32 degrees Fahrenheit. Steam point, 212 degrees Fahrenheit. Yeah, you need to know all of these. So here are our conversions. If we just remember these two, we should be able to work out any conversions. Celsius equals Kelvin minus 273.15, or you could remember this the way I wrote it earlier, that Kelvin equals Celsius plus 273.15. Fahrenheit is related to Celsius by 9/5 Celsius value plus 32. Okay, so the Fahrenheit is always greater numerically than the centigrade temperature. Okay. So let's do a simple problem. All these problems are really quite simple. They're just using formulae. I'll just talk you through it, and then you can solve it. Room temperature is generally defined to be 25 degrees Celsius. I apologize for this funny symbol. Not sure why it didn't come properly. That's supposed to be degree Celsius. What is room temperature in degree Fahrenheit? What is it in Kelvin? And I gave you the formula here. They are not normally given with the question, so you'd be expected to know the formula. What is the room temperature in Fahrenheit? We know Celsius. So we know this expression is what we need to use. We have 25 here, and we just need to find TF. Okay, use your calculator and get that value. What is it in Kelvin? If you know Celsius, you can always move to Kelvin. Which one is greater? Kelvin is greater, so you need to add 273.15 to this number, and you should be able to obtain your answers and check them against mine. So in Fahrenheit, you should get 77 Fahrenheit, and in Kelvin, 298 Kelvin. Now on 77 Fahrenheit, we say it's quite a nice warm day, not too hot, just nice and warm, like 25 degrees Celsius. Okay. Another problem. The surface temperature of the sun is about 5,750 Kelvin. What is this temperature on the Fahrenheit scale? So we don't have a direct relationship between Kelvin and Fahrenheit, but we're going to go from Kelvin, to centigrade, and then we can change from centigrade to Fahrenheit, right? So how do we go from Kelvin to centigrade? We're going to subtract 273.15. So this is two-step. There, subtracted it, and then use the formula up there to get 9,890 degrees Fahrenheit. Another problem, at what temperature do the Fahrenheit and Kelvin scales have the same numerical value? Okay, so this is just slightly more difficult. You want the Fahrenheit value, which is this, to be the same numerically as the Kelvin value, which is this. So you're going to substitute in just T for TK and T for Fahrenheit here. And instead of TC, put in this entire expression, yeah, as T minus 273.15. Let me write that out for you. So we want the same value, some value T, let's say, equals 9 over 5. And instead of TC, I'm going to write it in Kelvin. Yeah, so this is my Fahrenheit one. And the Kelvin value also we want to be the same. Plus 32. And this should do it for you. Simplify this equation, take all the T terms that side, solve for T, and then use your calculator, and you should be able to get the same answer as me. Okay. So work it out. You should be able to get 574.25. So 574.25 Fahrenheit is the same as 574.25 Kelvin. Yeah? Okay. Another question. Suppose the cold front blows into your locale and drops the temperature by 40 degrees Fahrenheit. How many degrees Celsius does the temperature decrease when there is a 40 degrees Fahrenheit decrease in temperature? So just a little more tricky way of doing this. The best way of doing this maybe is to find your, you have two temperatures, F1 and F2, and you know that F1 minus F2 is going to be 40 degrees in Fahrenheit. And you want to now convert F1 to centigrade, right? So you're going to use the formula to convert F1 to Celsius, which I gave you here. And you're going to do it again for F2, right? But there may be different values of Celsius. So you want to keep that as TC1 and TC2. And then you want the difference there between TC1 and TC2, okay? So do all the calculations and check whether you get 22.22 degrees Celsius. You can look through this if you're not able to do it, but I think you should be able to do this.